some information for people who may have had this course before and either finished or didn't finish the course. You do not have to pay all over again for an access course. When you enroll with your same username and password, and then you're going to see a little tab at the top of your home page that says enroll in another course. And you basically double click on this, and then it will ask you for your current course ID. And so that's where you enter Kavanaugh, whatever our course ID is, 73, blah, 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 okay? And if you need a number to call My Math Lab, there is a student number, and like for the first few weeks, they're there like 24/7 for you. So the student contact, or the student help number is 800-677-6337. So if anybody is having any problems with My Math Lab over the next, say, 4 or 5 days as you're getting used to it, that should be the number you call, and there'll be a very, a person on the other end that's like all too happy to help you out, okay? So let's start with rational expressions and domains. I did go in and I noticed that so far 11 people, and we have about 23 or 24 in the class, 11 of you have already enrolled into My Math Lab, and some of you have started homework. One person's done all of the prerequisite through almost class 2. I was amazed, so that was great. Others of you have enrolled, and there's a lot of blanks across there. Remember, P5 was what I asked you to do for today, so I'm starting in today assuming you did that. If you needed some help on these, oops, where'd they go? These problems, I assume you took the responsibility to go to the studio before class to get some help. If there's time after class, I can see you in the studio to do these, or I can help you individually, okay? So we're going to start with a new topic, probably to many of you. Maybe not rational expressions, but this idea of domain, you should probably highlight somehow on your notes, because this idea you will be working with over and over and over again this semester throughout the entire course, particularly when we get to what we call functions. When we get to functions, you'll be working with us all the time, the idea of domain. So let's start first with rational expressions. We'll define them and we'll work with them a little bit. So who wants to start us off today? Doug does. Thanks, Doug.
Rational expression. For example, following rational.
Okay, so the first thing I want you to notice is this is an expression, and it's because it's not set equal to something. It's not an equation, it's just an expression. And anytime you have the fraction bar, which indicates division, then you've created a ratio. And that's why I've underlined the word ratio in rational expression. So a rational expression is a quotient, which means you're dividing, or a ratio of two polynomials. So 250x is what we call a monomial. It only has one term. 100 take away x, one term. Anytime you have an addition or subtraction, you create multiple terms on either side. So in this case, we have two terms. So 100 minus x, any guess what that's called? If one term is called monomial, what two terms might be called? Binomial, right. So this is a binomial. All right, so in this case, we have a monomial divided by a binomial. And that's what this means, the ratio of two polynomials. Because even though these have special names like monomial and binomial, they still fit under the umbrella of polynomial. Okay? At your table, answer the following two questions and check with a neighbor or two. So I want you to find the cost. Right here is where X is defined. X is the percent of the pollutants that are discharged into the river. You can't do these expressions unless you know what X is. So find the cost in millions to remove 20% of pollutants, and then what percentage, so now you're solving for X, can be removed for a cost of 375 million. So work on those at your table. I'll give you some time and check with someone at your table, and when your table has a consensus of the two answers, put up your flag. So let's take a look at this. There's a couple of reasons why I chose this problem. One was for exactly the first misconception that I saw as I walked around the room, and that had to do with putting 0.2 in for X. And that's why it's so important, not only when you have a problem, to read how the variables are defined, but when you start solving problems, you have to say what your variable represents, or else it's meaningless. So X is the percent, X percent. So when you read this 20%, the percents are already taken care of with that symbol and that word. So X, the value for X is 20. So when you put 20 in for X and you solve this, what do you come up with? What, 62.5 million, something like that? 62.5. So right now, that's the answer. It has no units on it. So don't stick a dollar sign in front of it or put millions after it. You do that when you then write your sentence to respond to the question or the statement. So you can say the cost to remove 20% of the pollutants is, now you put on your 62.5 million. Okay, that's where you do it. When you solve an equation, your equation at this point doesn't have any numbers attached, units attached to it. Okay, now what percent of the pollutants can be removed for the cost of 375? It tells you that this rational expression describes the cost. So this thing that you're looking at is just like, you know, a neon sign saying, I'm the cost, I'm the cost, I'm the cost. So if you know what the cost is, 375, you can set that equal to 250 X over 100 minus X. Now, anytime you're working with any expression that has a more than one term like this, a binomial, always put it in parentheses. That will help you as you simplify or work with the equation. Now, when you see something like this, there's a couple of approaches you can take to remember how to do this. One approach is probably what some of you learned in an earlier algebra class, is that you have the right to multiply both sides of an equation by any expression as long as it's not zero. So you want to have a 1 in this denominator right here. So if you multiply this side by 100 minus X over 1, you have to do it to the other side, 100 minus X over 1. When you do that, you create the number 1, which we're going to refer to as a foo-foo, fancy form of 1. And so on the right side, you only have the expression 250x. And on the left side, you have 375 times 100 minus x. Now, I think you can all solve that equation for x, and you come up with x equals 60. Then you would write a sentence, 60% of the pollutants can be removed, blah, blah, blah. Okay? That's one way to solve that problem. Another way, in a way that US students are really weak at recognizing, is how to solve proportions. And this is a proportion. A proportion looks like this. It's two equal fractions. That's all it is. And you might say, but wait a minute, I don't see a fraction over there. Well, you can make it look like a fraction by just throwing divided by 1. Want to do me a favor? Just dump them all out so I don't hear the bag crinkling. Okay, thanks. All right. I'm like one of those people in a movie theater, right? If there's someone behind me eating popcorn in the back, I have to change my seat. It's just, there's a name for, you know, when you have really sensitive noise stuff. I have to sleep with a fan on too. So anyway, nothing, he didn't do anything wrong. I just had to do that because all I could hear was the bag crinkling. Okay, so does anybody remember how you solve a proportion? Yep, Mason? Doesn't matter when you learn it. Just tell me how you learn, how you solve it.
Well, first you cross multiply.
That's all I want. Yep. Okay. Thank you. A times D equals B times C. Good. All right. You can tell me afterwards when you learned it, okay? AD equals BC. That will always work. And all you have to do is just check out any two fractions you know are equal. It always works. Always. And I can show you the reason why it works later if you'd like to see it. Again, put that in parentheses. 375 times that is equal to, well, and because you have the denominator there, it's just going to equal your 250x. That's another way to do it. One last way to think about this is like a division problem. Here's an equation that defines a division problem. We learned how to check a division problem by taking the answer, multiplying it by the divisor, and seeing if we get the quotient, what we started out with, the dividend. So that's another way to do this problem. If you recognize that this is just a division problem because it's a rational expression. So you say, okay, I'm going to take my answer, I'm going to multiply it by my divisor, and I'm going to come back to my dividend. So that's three different ways to look at this same type of problem equation, how to solve it. All of you use different methods based on what you remember, what you didn't remember, but I wanted to just show you this because if you can ever simplify a problem into something you recognize, you can often construct the way for doing it for yourself, which is more important than my showing you how to do it, because you'll always remember that, okay? Okie doke, so I think we've got that answered. Okay, so I want to show you how your graphing calculator, so if you don't have a graphing calculator, just pay attention, and maybe one of your table mates will let you use theirs eventually. You can try it when we have some time to work. But we just filled in 20% for the pollutants, right? We just said when the pollutants are 20%, it was what, 62.5 million? So let's suppose I asked you a bunch of like 30, 50, 80, whatever, and you didn't want to have to go through that arithmetic and that, evaluating that expression over and over. Well, your calculator can do it all for you. So let me show you how to do that. The first thing you want to do with your calculator is to put in your rational expression right here and your y equals button right here. So let's put in our y equals button. And, first I got to turn it on. That always helps. Clear it out. Okay, so quit everything. So here we go. I'm going to clear everything out because that's from last semester. Okay, so y equals y1. We got a bunch of possible equations we're going to put in here, but we're going to say 250x is our x right there, divided by, and now this is where you have to use your parentheses or else it's not going to divide by the whole 100 minus x if you don't use parentheses. 100 minus x. Okay. Now what you do is a lot of students don't really recognize, yeah, go ahead. Oh, thank you. Well, I would have definitely screwed up, huh? Okay, second insert paren. Okay, there we go. All right, so what a lot of students aren't familiar with, they've used these to graph things, but they're not familiar with the table feature, which comes in really handy and can help you do a lot of things. So the table feature is, you see how it's yellow and it's above graph? Anything that's yellow on your calculator, you have to press the second button first. So the next thing the instructions say to do is press second yellow table set. Now table set's right here above the window because you're going to tell your calculator how many pollutants you want to actually remove. You're going to tell it where to start and what the increment is. So you hit second, and it's really second window, but it's table set above it. So you're going to say, well, we did 20. We might as well throw 20 in. You could start it at 20 or 30 here, whatever you want. Let's say 20 because that's the first problem we did. Now I could do 20, 21, 22, 23. Well, I'd be here all day up to 100. So this thing says, what increments do you want? What's the difference between 20 and the next number you want to see in the table? Well, the next number is 30, so I'm going to put 10 in there. So I use my arrow to go down and I put a 10 in there. Okay, so that means when I see my table, it's going to have the cost for 20%, 30%, 40%, 50%. Now, this is kind of an interesting thing right here, this independent. That means your independent variable. Your independent variable here is X. That's what you control. You control what percent of pollutants you put in there. Your dependent variable is your answer, cost. So one of the features you can do here is if you keep it on auto, when you look at your table, it's going to say 20, 30, 40, 50, 60, 70, 80, 90, 100. But notice you don't want exactly those increments. So you want to be able to ask it to compute a certain percentage. So you're going to actually scroll over and hit ask and then hit enter. The dependent variable, just keep it at auto. So now let's look at our table. Second table. And now it's going to ask, what percent of pollutants do you want to find the cost to have removed from this river? So the first thing in your table is 30, so just put in a 30. Hit enter, and there's your cost. So by removing only 10% more, we've gone up to 107.14 million. Okay. Now we don't care about 40. How about half the pollutants in the river? So where was it recently? Was it somewhere in Virginia that they had this big, people haven't had water, fresh water for like weeks. West Virginia, right? This big plant dump. I don't know if there was a leak or whatever. I don't know how long it's going to take to remove the pollutants from the river, but and from the water table, but it's going to cost quite. You can start to see how this cost is going to grow pretty quickly. Yeah, that's right. How long it's going to take for those people. Right now, 50, let's see, would be 250. All right, so what I'd like you to do at your seats is I'd like you to fill in the table, and if you don't have a calculator, you can come up here and use mine and fill it in. If there's a couple of you, come on up and fill it in. So you get a chance to use the calculator, or if someone at your table's already filled in, maybe they'll lend you the calculator. Denotes scientific notation. Okay, so what's happening to the cost as we get closer and closer to 100? What would happen if you were on a graph? What would be happening to your graph? It's definitely increasing, and it's going out the roof, right? It's just exploding. And so what happens when you try to enter 100? Did you try to enter 100 into your table? Let's see. Now let's find out. So I got two calculators here. Which one did I use? Here we go. To close that one. Just throw it down there for now. So let's put in 100. Error. So can't even calculate a cost. It's just gone like out of sight. Okay. So this tells you that it's pretty much impossible to get 100% of the river's pollutants out. So what happens in our expression if we actually try to put 100 into the denominator or into X? Let's take a look. If we actually try to put 100 in, we try to calculate this, we get some number on top that looks like this. And what number do we get on bottom? 0. And there's no number that defines that division. You can't put a number here that defines it. It's impossible. We can't divide by 0. That's why you got an error in your calculator. So what we say is that this rational expression is not defined. That's the word we use for the value of X equals 100. We can put any other real number in here, any other real number, and this expression will make sense. You'll actually get a number out in your calculator. You'll get it defined. Your division will be defined. So that is what leads us into the idea of what a domain is in mathematics. So an important concept you may or may not have seen before is that of a domain. Okay? The domain of an expression is a set. Okay, and this is where students, when they first see this, they just want to write the number that isn't in the set. because it's easier. But the domain is tell me all numbers that work for an expression so that I can evaluate the expression, or the expression would pop out a number for you. It has meaning. Okay, when we tried to put 100 in a minute ago, it had no meaning. It was an error. All the other numbers we put in, we got a cost. Okay, so the domain for this rational expression is the set of all real numbers with one exception. It's an infinite set, has an infinite number of possibilities, but this one won't work. X equals 100 will not work. So this is where we have to use our set builder notation from Monday's class to represent the domain. So the domain for this expression can be represented like this. The domain is the set, so we have to use those fancy braces, of all x such that, so there's your vertical line, x does not equal 100. Remember, we already determined that x is a real number. That's assumed. We're assuming x is a real number. Is any real number. So when we say the set of all x, we're saying every single number can be plugged in here except 100. So when I ask you for a domain, the most important thing is that you write something with those braces around it. It's got to be a set. Okay? And if you still don't have set notation down, and at first you have to write it out in all words, and you say the set of all real numbers except x equals 100, that's okay for me. All right? So you get to have some practice with this set builder notation. Any questions on the domain for this expression? Anything at all? All right, let's move on then. So when do we get into trouble? When can a rational expression not be defined or evaluated? What areas will get us into trouble when we evaluate an expression? What do we have to be concerned with? Mason?
When we have denominator.
Yeah.
The denominator can be
Right. So one trouble spot we're going to run into, is we have to make sure that our denominator is not equal to 0. So when can an expression not be defined? When the denominator is equal to 0. Okay. So can you give me an example? Oh, I said a function. Sorry, it should be expression. We haven't done functions yet. Can you give me an example of a rational expression that has a domain of all real numbers except x cannot equal 10? Can someone give me a rational expression? So that means I've got to put a fraction bar there, where the domain is any number, but it can't be 10. Can't be 10. Yeah, Chris? Yeah. 10 minus x. Anything over 10 minus x. Do you see how that would get you into trouble? Because if x were 10, we'd have a 0 downstairs. So the domain for this is the set of all numbers x except x can't be 10. So you're kosher as long as you're any number in the whole wide world except for 10. Any questions on that before we move on? All right, so let's see what's coming up next. All right, so we've got some rational expressions here. And I'm going to do the first one for you, and this is why you needed to review your factoring. So we said that we set the denominator of a rational, oops, I keep calling it function, sorry guys, expression, equal to 0 to find the number on numbers. Sometimes there's more than one number that must be excluded from the domain. So find all numbers that must be excluded for the domain and then write the expression. So I don't have any concern at all about the numerator being 0. It's fine to be 0 in the numerator, but your denominator cannot be 0. So to find the value that you have to exclude, you set the binomial that's in that denominator equal to 0, and you solve. So this is the difference between two perfect squares. x squared is a perfect square and 25 is a perfect square because 25 is 5 squared. So these are the fun ones to factor because they look the same, x, x, 5, 5. The only difference is their operations are different because notice you don't have a middle term there. You don't have 5x, 10x, or anything like that, so it's just plus and minus. And now you say, for this multiplication problem to equal 0, I have to find out when x plus 5 would equal 0, and I have to find out when x minus 5 would equal 0. So x plus 5 equals 0 when x equals negative 5. And x minus 5 equals 0 when x equals positive 5. So there's two numbers that are not allowed entry into this club, 5 and negative 5. So the excluded values you can write right here. You can't be plus or minus 5. They're excluded. Okay? They're grounded. The domain is a set. So it's the set of all x such that x does not equal plus or minus 5. Okay, so I'd like you to work together on the next rational expression. If you need to, you all have boards beside you. That's why I had the boards put in the room. Feel free to get up and work on it together. And work on both finding the excluded values and the domain for B. So looking around at the boards, people were able to factor this. First of all, this is called a trinomial because it has 3 terms. So chances are, if you can factor this, if it's not prime, you're going to be able to set 2 binomials up, x and x. And this is how I read this. I'm looking, I don't pay attention to the minus sign yet, the subtraction. I'm looking for factors of 16. So off on the side, I do 16 and 1, 8 and 2, and 4 and 4. And then I read, because I know that my 2 numbers are going to be plus and minus because it gave me a negative answer. If I add a positive and negative number, it's just like subtracting them. So this is how I shortcut the factoring process. I say I'm searching for factors of 16 that differ. And then I just look at that middle number that differ by 6. And then I deal with my signs. So right away I zero in on those 2 numbers, 8 and 2. They differ by 6. So I know there's going to be an 8 and a 2. And now I deal with the fact that my middle term is negative 6x, which means my bigger number must carry the negative sign, and my smaller number must carry the positive. So I just go minus, plus, I'm all done. Okay, for factoring. Now I set that equation, which is a multiplication problem, equal to 0. And I say, if this is a big 0, then the whole thing is a 0. So that's going to equal 0 when x is 8. And if this thing is a big 0, that multiplication problem will be 0. So if x equals negative 2, that will be 0. So my excluded values, the values that are not allowed into the club, are 8 and negative 2. And my domain is a set of all x such that x cannot be 8 or negative 2. Okay? Any questions on that after you've got through working together or by yourself individually? Anything before we move on? I don't want you to have a question. So we'll just multiply if you don't ask now. Anything at all? All right. Well, the next part of this is I'm going to talk about reducing. Well, first we're going to start off with arithmetic, reducing a fraction, which really is a rational expression, but we didn't go around calling 12/15ths rational expressions. So, but it is a rational expression. So let's understand the idea behind factoring. So what I want you to do is to reduce this. Just do it right now at your seats. And I'd like you to show the factoring of this into prime factors. Factor each number into prime factors if you remember how to do that. Even if you know how to reduce it. I'd want you to try it. See if you can factor 12 and factor 15 into prime numbers right beside it. And you might be able to get a little help from your friends. Remember, the prime numbers look like this. You won't need much beyond what I have here to do this problem. So these are the beginning of prime numbers. Okay. So what did we reduce this to? Alicia, can you help me with that one? 4/5. So what most people do, right, when they have something like this, is they might do something like this and they write 4/5. That's what a lot of people do, is they put those slashes. Some people do it in their head and they just write this 4/5. Okay. And when I work with people that never really understood what was going on when they're reducing, it's really important, even though you say, I don't really need to do it for numbers, but for algebra, it's going to be critical, is that you need to really look at each factor, each prime factor of the numerator and each prime factor of the denominator. So if we were to prime factor 12, we would have 2 times 2 times 3. That's 4 times 3. And each one of those numbers is prime. They can't be written any other way. And then we have 3 times 5. So when we reduce this, what we're really doing is we're dividing 12/15 by the number 1, which doesn't change it. I'm really taking 12/15 and I'm dividing it by 1. In that form, that's my fancy form of 1. That's my foo-foo. So there's my 4/5. And the way we do that is we write those slashes through the number. There's my number 1. Okay. And a lot of us say we cancel it, and it's fine to say cancel common factors. This is called canceling common factors of 1. But I would like you to try to change some of your habit, canceling the common factor, to add of 1. So you really recognize what you're doing. And that's going to be important in just about 30 seconds when we get to the algebra. Okay? So this idea of finding a common factor of 1 is called foo-foo. It was developed by this man, Aaron Einstein, in the 1999 Math Teacher's Journal. So we're now going to be simplifying these. And this is what happens. I actually had to teach a Math 090 class yesterday because the teacher was sick. And we were talking about some stuff, and I was showing them how what they were doing in arithmetic is totally related to algebra. So you look at this first problem, and you may not right now see any relationship to 12/15. It may look totally different to you. And sure, I agree with you, it does look different. But the idea behind how you reduce this kind of fraction, an algebraic fraction, and how you reduce 12/15 is absolutely no different. Okay, we're going to factor the numerator into its prime factors just like we did with 12, and we're going to factor this. Now here's the first word of caution that I'm going to give to all of you. I make up little stories, you'll notice as we go along. And with my 096 students, when they start working on this, I said, to keep you safe, because what doesn't keep you safe if you start doing stuff like this? This is like, what can I say? Do you see any multiplication between these 3 terms up here? No, it's all adding and subtracting. What you do with adding and subtracting in algebra is very different than what you do with multiplying and dividing. So you're not just looking for the same thing. That's one of the errors that we have when we're doing arithmetic. We're looking for the same factor. So everything has to be multiplied. Right now, everything is added and subtracted. So the first thing I tell my 096 students to do, that's not what I tell them to do, but that's pretty cool. How'd that happen? Wow, anyway, that was kind of cool. All right, so the first thing I tell them to do to make themselves safe from error is to put their arms around the numerator and denominator, just like that. And unless what you see in the numerator and the denominator are exactly the same, no slashes are allowed yet. Avoid the temptation. Now you take each one of these and you factor them into prime factors. That's why it was so important that you reviewed P5. So the factoring of the top, factors of 10 that differ by 3. What are the factors of 10 that factors. 7 times 3 doesn't give me 10, but I know what you were thinking. You were thinking of 7 plus 3. How about, that's all right. Okay. All right. I was going to try to get Summer to, okay. Summer, factors? Yeah. Okay, you can think. Paul, okay. Now, what about plus and minus here? Well, my 3x is positive. That means my 5 is plus, my 2 is negative. Bottom, factors of 8 that differ by 2. What are they? 4 and 2, plus and minus. Now, everything in the numerator is a multiplication form. Everything in the denominator. Do you see a fancy form of 1? Do you see a foo-foo? Do you see a common factor of 1? 2. I don't see a 2 anywhere. Oh, x minus 2. Oh, okay. All right. So you can go like that. There's your 1, and you reduce it. Keep your arms around it, because sometimes you do all this work, and when you don't put your arms around it, what do you think the temptation is? Yeah, you cancel out the x's, right? Okay. So that's done. That's your answer. So I put this one in to try to see if that evil temptation lurks up in you. If you put your arms around x plus 8 and x plus 4, you say, these aren't the same. I can't factor x plus 8. This is already reduced. Already simplified, silly. That's what I say. Already reduced. All right? All right. Okay. So let's take a few minutes and summarize, including examples, how you add, subtract, multiply, and divide fractions. So that's going to be up to you right now. I'm going to give you 5 whole minutes to write your own examples. Talk about it with your group if you want. How you add, subtract, multiply, and divide fractions. And if you don't know and someone has a book, open your book. And we're going to do a subtraction problem together, because those tend to be the 2 hardest for people. Okay, so let's take a look at this first one. Now, before you even attempt to do any of these problems, factor everything to death. Okay, factor everything to death. So you want to factor your first numerator. It's the difference between 2 perfect squares. We've already seen x squared minus 25 today. Guess what? Your first denominator is also the difference between perfect squares. 16 is a perfect square, and so is an x squared. So I'm going to factor both of those. Now, division can be written as multiplication. Division changes to multiplication by the reciprocal of the divisor, which is the expression you're dividing by. So this problem can be rewritten as this multiplication problem. So now when I multiply, so since I'm multiplying and I multiply straight across, I just put one big fraction bar. I have x plus 4 on the top because this denominator goes upstairs and this numerator goes downstairs. This changes to multiplication. So now I have to factor x squared plus 6x plus 5, which is x plus 5 and x plus 1. So notice it's just one big fraction now. That's all it is. Everything's completely factored, and now you look for your foo-foos. So you have an x plus 5 there and an x plus 5 there. That's just the common factor of 1 that I'm dividing out, and an x plus 4 and an x plus 4. Do I have anything else? No. So what am I left with? Parentheses, x minus 5 over x minus 4 times x plus 1. Done. You do not, for me, have to multiply out the denominator. You don't have to call that x squared minus 3x minus 4. You can just keep it like that if you want. Okay? Because why avoid making any errors when you've already factored it correctly? Any questions on this? Okay, I'm going to do the next one, and then I've got a couple of problems for you to try before you leave in 12 minutes. Subtraction. If your denominators are different, you have to find the lowest common multiple. When you have numbers, often you'll just know the lowest common multiple of 3 and 10 is 30. You just know it because you've worked enough with numbers. So I'm going to give you a technique. I can't take 3 classes or 2 classes to do this like I do in Math 096, but I'll show you the approach that I think is very helpful. So before I would do anything, the first thing I would do is I'd put parentheses around each denominator. And then the other area that really messes students up with subtraction is that they forget to distribute the negative sign when they have the distributive property. So right now, what I would do is I would change this subtraction of 2 to adding, and I'd put the negative right there in front of 2. That way, when you have to multiply the negative 2, you won't forget it. You won't have it sitting out there between the two fractions and just forget about it. So the first thing I'm going to do is to factor each denominator, and I'm going to put them in colors, each factor in a different color. So this is x plus 2 and x minus 1. I have two different prime numbers there, two different prime factors, just like if that was 2 times 3 and the denominator was 6. The next one is x minus 4, which is different than any of the other factors, x minus 4. And then I have x minus 1. I already have an x minus 1. So you see they share a factor. Okay, they share a factor. The factor that they share is x minus 1. When you create a lowest common denominator, or which is really a lowest common multiple, all you're required to do is to put in each different prime factor you see. Okay, and because they share an x minus 1, you don't see any x minus 1 square anywhere. All you're required to do is just put it in once, just like the reunion with the Beatles. You basically do a reunion here. You say, okay, my first denominator is x minus 1 times x plus 2. And I'm going to put that in a circle. When I go to write my second denominator, x minus 1 is already a member of that. So I'm just going to grab it like this. And my second denominator is x minus 1 times x minus 4. So they share. The x minus 1 belongs to both of them. So your LCD is just multiply straight across. You need an x plus 2. You need an x minus 1, but only one of them. And you need an x minus 4. So this would be like 2 times 3 times 5. This would be like the multiple 30, except for it's in algebra. Okay? And now if you recall, you have to change each one of these fractions to an equivalent fraction with the common denominator. So that's why you want to have everything factored. So you look at your first fraction, which looks like this, and you want to change it to an equivalent fraction that has x plus 2, x minus 1, and x minus 4 in it. Okay? So you compare the two denominators, and you'd say, to go from this denominator to this denominator, they both have x plus 2's, they both have x minus 1's, it's missing a factor of x minus 4. So I'd have to multiply top and bottom only by 1, and the 1 has the form of x minus 4. So my first fraction can be changed to this fraction with that common denominator, x minus 4. And this is where I get a little lazy. I just put LCD, just like that. Plus, now I have a negative 2, and I'm going to multiply negative 2 by something. So let's look at the second fraction there. We've got negative 2 over x minus 4 times x minus 1. And we want to change it to this denominator. So the factor that's missing from this fraction to this fraction, they both have an x minus 4, they both have an x minus 1. You have to multiply top and bottom by x plus 2. So your equivalent fraction is negative 2 times x plus 2. See why it's important to have that negative there? Because if you kept that as a 2 and the negative was out there, when you go to multiply, you're going to forget to distribute the negative. So now they both have a common denominator. Just write one fraction bar like that. And you just drop your parentheses here. Nothing's happening with x minus 4. And now distribute your negative 2. You get negative 2x minus 4. So that equals negative 1x minus 8. And then you put in your LCD in all of its glory. And you can feel really proud of yourself because you've just added and subtracted algebraic fractions. Chris? Oh, yes, thank you. Oh, I forgot the x. I forgot to put the x here, sorry. So it's x squared minus 4x. Okay. See what happens? I'm looking at the clock and I'm hurrying. Woo. Okay. So what do I get? X squared minus 6x minus 4. That can't be factored. So you're going to just put it in parentheses. It's prime over that LCD. And then you're done. Okay. Yep, Chris? Sign? Plus negative. Right. Yep. No, because to make a fraction negative, all you have to do is make either the numerator or denominator. If I made both of them negative, then I'd be changing it right back to where it was. Good question, though. Okay. All right. So those will take you some time to do. Trust me, they will take you time to do. They're just labor intensive. I didn't give you that many for homework. So at your table right now, you have 5 minutes to answer these. True or false? If false, you got to change it or show a counterexample. When your table has it done, put up your flag and I'll come over and give you the okay.